Before I get started with the lecture, let's see. I want to share. So I'm going to share the Brightspace and show the class something. Let's see, where is it? Find it. Here it is. Okay. If you go into the course under uh, the syllabus, course schedule and due dates, the one that's posted there is the one that has assigned June 19th as a holiday. But since the governor has not designated June 19th as a holiday for Juneteenth, um, I'm going to go by a new schedule. And I've got that schedule. Just scroll down to alternate schedule. There's your alternate schedule. And it's going to look exactly like the other one with slight changes in what we're going to do. Take advantage of that extra day now, June 19th. Okay, stop this share and get into the course. Okay. Make a slideshow. Okay. So after we completed our study of chemical kinetics, how fast a reaction goes, um, let me start with the energy diagram for a reaction. Right. This is progress as usual, and this is the energy of all components. So let's say it's endothermic reaction. So we start down here with reactants. And we go through a activated complex. We need activation energy, and then we end up with products. Okay. I've got a slide on this, but I thought this would orient us. Okay, what we were discussing in chapter 12 was kinetics, and everything having to do with kinetics happens in here. Okay. What we're going to talk about in chapter 13 has to do with this part and this part. That's equilibrium. Equilibrium is a condition of actually of any process, but in our case, we're speaking of equilibrium in terms of chemical reactions, is where you're only concerned with where you started and where you end up. How you get there is kinetics. So equilibrium says we're trying to establish a ratio of reactants and products and try to understand where we're going to end up. Let's see. That's being shared, but okay, I'm not seeing it on my screen. Hold on. There we go. Okay. So that being said, um, these two avenues of study in chemistry occurred at approximately the same time. There were some scientists that were interested in the rates of reaction. Some were more interested in equilibrium. And this was at in the middle of the 19th century, 1850s, 60s, 70s. But the tools for understanding and quantifying kinetics were not very well developed. Whereas the chemical equilibrium, the tools for chemical equilibrium were much simpler. So it tended to develop first. But we study kinetics first because the understanding kinetics tells us how equilibrium progresses. So on the macroscopic scale, what we observe from outside is that at equilibrium, you don't see any change. You don't see any change in the concentration of any reactants that are left over and products that are produced. So it seems to be static. That's what we observe. But on the molecular level, we know from kinetics that the forward reaction is occurring at unbelievable speed, but the reverse reaction is exactly balancing it when we reach equilibrium. Now, during our study of kinetics, we studied primarily at the beginning of the reaction. So we only had reactants and no products. And I mentioned at that time that the reason we do that is so that we don't have any competing reverse reactions. But the reverse reactions do occur, and more as you produce products until you reach a state where the forward and the reverse reactions are exactly balanced. This is actually a dynamic situation, a dynamic equilibrium, rather than what we would perceive as static. All right, I've already said that. So if we actually measure the concentrations, and here, our example here is the Haber-Bosch equation, nitrogen plus hydrogen yields ammonia. Notice that at time zero, we have nitrogen, a concentration of nitrogen, and hydrogen, but no ammonia. That's the point at which we want to study kinetics. But as the reaction proceeds, we gain more product, ammonia, and we lose hydrogen and nitrogen. And we lose them in a ratio that is consistent with the stoichiometry. Okay, I've already said this. So I'll just leave that up there long enough to be recorded and move on. So I don't want to repeat myself. Okay, this is another way of looking at it. If you look at reaction rates in terms of the rate equation, right? How fast is our reactant disappearing? And we could also look at it as how fast is the product appearing? And the rates are going to change with concentration. So as you decrease the reactants, the rate's going to decrease. As you increase the products, the reverse rate is going to increase until they meet in the middle. And that's the point where the forward rate equals the reverse rate. Okay. So let's consider this reaction. Water plus carbon monoxide yields hydrogen plus carbon dioxide. What do you think would happen if this reaction is at equilibrium? Right? It appears to be static. In other words, the forward reaction is equal to the reverse reaction in terms of rates. Now we're going to disturb it. We're going to add water. So we're going to add more reactant. What would you expect to happen? If we add more reactant, then there's going to be more, go back to the kinetic molecular theory, where impacts are required for a reaction. If you add more reactant, you're going to get more impacts. So the reaction rate should increase toward products if we add a reactant. Now that's as long as you've got enough of the other reactant in there to make the reaction go. But we're assuming that at equilibrium, you still have some product and some reactant. So what's going to happen? Well, the reaction rate's going to increase in the forward direction until you produce enough products so that the reverse reaction now rebalances the equilibrium. Similarly, if we add product on the product side, in this case, hydrogen, then we're going to increase impacts and reaction rate on the product side going in reverse. So then that'll continue until we produce enough reactant. So the forward reaction exactly balances the reverse. So it's like a self-balancing situation. Now this, unlike kinetics, remember the rate law for kinetics has to be experimentally determined for the overall reaction. But for equilibrium, we can take advantage of the balanced equations, the stoichiometry of the equation. This work, this law was proposed by the work that was done by two Norwegian chemists, Peter Weg and his brother-in-law, Cato Guldberg, about the time the Civil War was winding down. And what they wanted to do was solve problems in equilibrium. They needed a mathematical description so that they could quantify the players in the reaction. And they produced, well, they called, when they discussed kinetics, they called it chemical dynamics. And when they discussed equilibrium, they call it chemical statics, which is still, those two terms are still used, not in chemistry, but in physics. So when you first study physics, you studied statics, where there's no motion. There appears to be balance everywhere. And you study how the balance is maintained or offset. And then you move into dynamics. But for chemistry now, we call dynamics is chemical kinetics, and statics is chemical equilibrium. Now, the equation is developed in terms of concentrations. Absolute amounts, things that cannot be quantified as concentration, do not enter into the expression, the mathematical expression. And this is how it looks. I'm going to, even though it's there, I'm going to put it on the board so we can talk about it. So if you have two reactants, and it doesn't have to be just two. This is a hypothetical. Forward and reverse reaction produces this product and this product. And these are the coefficients, A, B, C, and D, small letters. Then at any given temperature, at a temperature, and the temperature can't change for this equilibrium to work and this equation to be valid. If you change the temperature, then you're going to change the expression and give you a different K value. Weg and his brother-in-law came up with this reaction. They said these terms will be in the numerator. So the concentration of C to the little c power times the concentration of D to the little d power now is divided by the reactants. So that's the law of mass action. These are concentration terms, and the square brackets are used. And when you see square brackets in this context, that means equilibrium concentration in molarity. Okay. Now we can write this expression with using other types of concentration expression. Instead of molarity, we could use partial pressures, right? For gas mixtures. We don't have to. We can still use molarity. We can use partial pressures, or we can use, you could use molality too. Any units of concentration at equilibrium are expressed here, only the square brackets are reserved for molarity. The other thing that we do here, well, there are a couple of things. Let's move on to the next slide. I think I've got them listed. Not yet. Okay, so hold that slide. So this is going to be molarity. And we have to express things in terms of concentration. What phases of reactants or products do not change concentration during a reaction? Solids and pure liquids. If you have a solid or a pure liquid in any of these reactants or products, that term does not show up in the law of mass action because the solid doesn't change concentration. I mean, it might disappear, it might reappear, but its concentration doesn't change. Pure liquids, their concentration doesn't change either. So if you see any reactant or product in here with a phase of S or a phase of L, you don't put it in the expression. Only gases and anything that's can change concentration, like solutions, for instance. The other thing is, you'll notice that when we do the expression and we express the K, there are no units. And that's out of practical consideration, because if you've got units of concentration and you've got coefficients in here that can be anything, then when you take these to the power, then the units of measure can be just, the sky's the limit. It would be unwieldy. So we don't report the units for the K value. This is an equilibrium constant. Sometimes it'll be written this way, right? So we don't include units in this number, but we are extremely careful in particular about our calculations so that the units are not an issue. Okay. Other types of constants, there are subscripts that are reserved for certain types of equilibrium constant. This one, Kw, is the equilibrium constant for the dissociation of water. Right? We'll talk about that later when we get to acids and bases. If it has a Kp, that is an equilibrium constant calculated in terms of partial pressure. So we would say something like this. If these were all gases, right, and we wanted the Kp expression, right, then we would have the partial pressure of C. So we have P sub C, the little c power, times the partial pressure of D to the little d power, and then the partial pressure of A to the little a, and the partial pressure of B to the little b. Now, it's important that we know how this is calculated, so that's why the subscript is important, because that way we put these in terms of usually atmospheres. There are other Ks like KSP, solubility product. We're going to get to that one in a subsequent chapter. And there are some others. Now, what if, remember in Hess's law, we combined equations to get the target equation. and we could calculate the enthalpy. That was in the first semester. If you combine equations and you're looking at equilibrium constant for the final equation, we can still add those equations together. But how do we get to the overall equilibrium constant if we know the individual constants for the component equations? Well, we need some rules. And the K for this equation, if we reverse the equation and we write the equation, let's see, let me make room here. If we write the equation this way, in reverse, then the K here would be A and B and then C and D. Now, how are these two related? Right? This one is obviously the inverse of that one because we put the denominator in the numerator and the numerator in the denominator. So this K is equal to, let's see, this, let's call this 1 and this 2. That's equal to the inverse of K1. Okay, that's what that means. That -1 means inverse. All right. So why would we even want to do that? Well, if we're going to add the equations together, sometimes we do have to flip the equations, right? Remember that from Hess's law. Also, we may have to multiply the equation times a constant in order to, before we can add them together. So what would that do to the K if we had to multiply this equation through by, well, I don't know, let's just make a number, say 2. Right? What would that do? Well, this would be 2D, right? This would be 2C, 2A, and 2B. Okay. Here's Ann. All right. So that's what would affect the constant. So what would this expression be now? Well, we could factor out, right? Go back to math class. Factor out the powers. This is the same thing as little c, d, d, and over a, b, the whole thing squared. Okay. So then what would this conversion be? Well, the equilibrium constant for this equation now would be equal to that first one squared. Right? You take the original and apply the multiplier. So if we used a half instead, it would be to the half power or the square root. All right. So that way we can manipulate equations and then we can determine the overall K for the reaction. But so far we've only done individual, like component equations before we add them together. What happens when we add these K's together? When you add those K's together, was it on that slide? I missed it. I missed it. The overall K, well, okay. I'll just tell you what it is. If you have a K, have several K's here for these reactions, the overall K is equal to the product of those K's. You multiply all the K's together. And if you're going to add those equations together, then the overall equation will have a K that's the product of the individual Ks. Okay, so we're going to say this again. As long as the temperature is constant, then the K is constant. It never changes unless the temperature changes. Now, there's also, let me see, erase this part. I have room to write. There's a difference between the equilibrium constant versus position. Okay? The constant is exactly that. For any given temperature, constant temperature yields constant K. That's redundant because K is a constant. You don't have to say constant K. The K doesn't change. The position, on the other hand, depends on starting or changing conditions of concentration. So you may start off with, say, 1 mole here and 1 mole here, and you let the reaction run. And it gives you a concentration there, there, and some left over here. Calculate your K, that's a constant value. But if you start off with 2 here and 2 here, and maybe a half mole there and a half mole there, half molar, then the reaction is going to reach equilibrium, and the K is going to be the same. But the end concentrations at equilibrium, these concentrations will be different. Okay, that's the difference between constant and position. Oh, okay, so here are some, I gave you a few. I missed Ka. Ka is the acid dissociation constant. We're going to get that in chapters 14 and 15. Chapter 16, we'll get the solubility products and formation constant. And then Kp is based upon pressure units, usually atmospheres. Okay, so here's an example. Let me see. I need to make some room, don't I? Let's just wipe the board clean and start over. Okay, so here's the Haber-Bosch process again. And we're given 2 types of equilibrium expression. One on the right uses molarity. One on the left uses partial pressure. And we keep all of our terms because we're talking about gases. And gases will change concentrations as the reaction proceeds. Now, if we're given these values for partial pressure at equilibrium and a given temperature, then we can calculate the K sub P using these terms of atmosphere. All right, if we do that, then we get this value. Kp equals 3.9 times 10 to the 4th. So we've got this equation. In equilibrium with this product. And we calculated the Kp equal to 3.9 times 10 to the fourth. All right. Now we can, these constants are interchangeable if we use this equation. If we have this Kp here, then it's equal to the equilibrium constant in terms of molarity times the gas constant, right? And since these are in atmospheres, this has to be the 0.08206 liter atmospheres per mole K. Whatever the temperature is, right? Why do we need the temperature? Well, we have to cancel temperature out of the constant. Constant has a temperature term in it. So we need the Kelvin temperature also. But this term is change in number of moles. So remember, delta means after minus before. Right? So after is 2, and before is 4. Right? So that's equal to minus 2. So this term for that equation would be equal to minus 2. Okay? We have to be given the temperature, and we've got the Kp. So now we can calculate the K in terms of molarity. And if we do that, we come out with a K equals 2.5 times 10 to the 7th. Okay? So they're different numbers, but they tell us something about the equation. Notice that these numbers are very, very large. These numbers are huge for this given temperature, 35 degrees C. This is at 35 degrees C, which is 308 K. Lost my train. Oh, you'll notice that both of them are very large numbers, which means what? If you understand what they represent right products over reactants in concentrations. Okay, so what does that tell you? How do you get a large number using a fraction? You have either or, very, very small reactant value, very large product value. So what that tells us is for this enormous number, this reaction at that temperature goes virtually to completion. It produces mostly product, and there's not much reactant left behind. Now, remember, this is an equilibrium situation. So at 35 degrees, how fast is this reaction going to go? We don't know. This information doesn't tell us how fast it is. It just tells us what the equilibrium is. When it reaches equilibrium, it'll be mostly on this side. But you might have to wait centuries to get there. Okay, that's the point. We're talking about before and after, not in the middle. How fast does it get there? Okay, we can classify equilibria in terms of the mixture of phases. So if we have all the same phase in reactants and products, and the Haber-Bosch process is one of those, where everything is gas, all gases. Or for another reaction, maybe all are in aqueous solution, like this hydrocyanic acid ionization. Those are homogeneous equilibrium because all the reactants and products are in the same phase. as opposed to heterogeneous equilibrium, where in the first one, where potassium chlorate is in the solid phase, and the product, potassium chloride, is solid, and the other product, oxygen, is a gas. They're different phases. Or when we electrolyze water, split it into hydrogen and oxygen, we're working from a pure liquid and we're going to gases. So those are both heterogeneous equilibria. Now, what if we were to write the equilibrium expression for that first equation? Okay. Well, let's see. Products, we got a gas and a solid. Remember, the solid we do not put in the expression. So we only have concentration of oxygen to the third power. Okay. What about the denominator, the reactant? It's a solid also. So that's it. That is your equilibrium expression for that first equation. Okay. I wasn't looking ahead, so this slide also tells you the same thing I just put on the board. Okay, and this also, this slide and probably a couple of subsequent slides talks about how to interpret qualitatively the K value for a reaction. If it's much, much larger than 1, the reaction goes essentially to the right. Equilibrium lies far to the right. If it's a very small number, much, much less than 1, then the equilibrium lies with the products. Now, some books will tell you that if the K is equal to 1, you have an exact balance. But I take issue with that because the expression has powers, coefficients and powers, right? You may not end up with an exact 1. When you have an exact balance on either side, you may end up with a value of K that's small or large. That's why we say when it's much, much greater than 1 or much, much smaller than 1, then you're pretty safe in drawing that conclusion for the outcome. Okay, so if the equilibrium lies to the right, the value of K should be greater than 1. If it's to the left, it should be smaller, much less than 1. All right. So up to this point, we've used the law of mass action to quantitatively describe a chemical reaction in equilibrium. But what if, excuse me, you put several reactants and products together in different concentrations, and maybe it's not in equilibrium at that point. In fact, if you try to introduce reactants and products together to establish equilibrium at the beginning, you're likely going to fail because of experimental measurement error. But if we want to know which way is a reaction going to go, if you put so much reactants together and so much product together, is it going to go back toward reactant or is it going to go toward product? Well, that's where the Q, the reaction quotient, comes in. And the reaction quotient looks like an equilibrium expression. So if I use our original hypothetical equation, we would have C and D on top, but instead of square brackets, we use parentheses. Right? And we can calculate a Q value with the concentrations that we establish at the beginning. So now we need to interpret that Q. Compare the Q If the Q is equal to K, then there's probably going to be little or no movement. Okay. How about Q greater than K? How would Q, let's see, how would Q be greater than K? Well, the only way that Q could be greater than K is if the products were too high and the reactants too low. That would make Q greater than K. Okay? And if Q is greater than K and you've got too much product, the reaction is going to shift back to the left. Now, when I say shift left, shift right, that's based upon an equation. Right? If you write the equation backwards, then shift left is wrong. It should be shift right. Okay? So whenever you say shift one way or shift the other way, you must reference a balanced equation. If you don't, then I don't have any idea what you're talking about. You cannot, okay, the point is, you cannot assume that your reader understands where your shift comes from. You have to tell them. And the other way, less than K, the only way Q can be less than K is if it doesn't have enough product. It has too much reactant. Then it would shift right. Based upon the reaction equation from which we derive that expression. Okay. So let's clear this. Say we've got this reaction where we have iron 3 plus ions in aqueous solution reacting with thiocyanate ions in aqueous solution, and they're in equilibrium with the complex ion that forms from them. And that would be 2 plus. Is that right? Yeah, 2 plus. Okay. So this system is in equilibrium. We're going to use this reaction in not the next lab, but the one after that. The next lab is kinetics. The one after that will be Le Chatelier's principle. And we're going to use this reaction where this is kind of an orange color. This is colorless. And this is brick red. Okay. Now, in this case, we're given 6 molar as a starting condition and 10 molar. Let's see, or is it, yeah, 6 molar and 10 molar at a start. And then we end up with an equilibrium concentration of this ion at 4. You're probably wondering why I wrote it down there. We're going to introduce the concept of the ICE table. This is not Immigration and Customs Enforcement. ICE means initial, change, equilibrium. Okay? If we're going to calculate the equilibrium constant, we have to know what this value is and what that value is. And we're going to deduce these values based upon the outcome here. All right? Notice these are 1 to 1 to 1. So if we end up with 4 here and we started with 0, right? We put those two together first. We didn't have any product. So how did we get to this one? Well, we had to add 4 molar to get there. Okay? So how did we get that 4 molar? It had to come from here in the same ratio. So we had to lose 4 molar here. And these are 1-to-1, so we had to lose 4 molar here. Right? Okay. So now we can calculate what's left over. Right? 2 molar and 6 molar. Now we can set up our equation. Right? KEQ equals 4 to the first power divided by 2 to the first power times 6 to the first power. All right, so that's 4 divided by 12, isn't it? And that's 0.333. So that's our KEQ given this data. All right. And there's our ICE table and the calculation, and we should end up with 0.333K. Okay. Now that we have the equilibrium constant and we know the expression, right? That one divided by this one times that one, then we can change these concentrations here, and we don't know that one, and we can still determine what the outcome will be. What is the equilibrium position? Based upon this constant that we just calculated from this experiment. All right, so let's change our conditions. We're going to keep this value, KEQ equals 0.333, and that's equal to, we'll just put it right up here, 2 plus divided by iron and thiocyanate. Okay. So now we've got a new set of conditions. And I find it most convenient, rather than just writing a new table, is to write the balanced equation right up there and then put all of your terms underneath each one, as long as they're changing concentrations. If they're solids, you don't need anything. Okay, so initially we start with 10 molar iron. Right? 10. How many? Just one. 10 molar and 8 molar. And at the same temperature, right? That's important. If it's not at the same temperature, then this value is invalid. And we want to determine what's this concentration right here. Okay? So, starting from 0, which way is this reaction going to move? This one's easy. There's no product, so it has to move that direction. You don't have to calculate Q in this case. So, if we're going to move that direction, we're going to produce X over there. Right, that much. Right, we're going to use a little algebra. So how did we get there? Well, we lost X from this side because they're 1 to 1 to 1. And we also lost an X on this side. Okay? So at equilibrium, we're going to have 10 minus X and 8 minus X and X. So we put those values into our expression, 0.333 equals X, excuse me, maybe I better use brackets, square brackets. Be consistent. Like that. We're going to have 10 minus x and 8 minus x there. Okay. We've got an equation in one unknown. That means we can solve for it. It may not be easy because you'll notice what happens when we factor this equation, we end up with a quadratic. Okay. So we multiply these two together. Remember how to multiply a quadratic. This one times this one, that one times that one, then this one times that one, and this one times this one added together is the middle term. And then it's divided into this one. So we have to resolve that one also. All right, just to save time, this is going to come out with an equation of, let's see. Remember, if you use the quadratic solution for an equation, right? And I got it on the back of my calculator because I can never remember it anyway. Where is it? I got it back here on my calculator. You have to have your expression in terms of the coefficient of x squared, then the coefficient of x, then the constant equals 0. So once you get to that point, we're going to have this equation and then minus 699x and then plus 26.64 equals 0. Then we can use our quadratic equation, right? X equals minus b plus or minus square root of b squared minus 4ac all over 2a. So this is a, this is b, this is c. We go into the equation like that. And you're going to get two numbers, right? You can resolve this number, and then it's going to be plus b or minus from b. And either one of them divided by 2a. So that's going to give you two different values for x. Then you have to decide which one is valid. So in this case, we got x could be either 15.99 or 5. All right, which one makes sense? Well, if x is 15, you can't subtract 15.99 from 10 and get anything. You get a negative number, right? So that's out. The only one that works is 5. So the concentration of iron thiocyanate ion is 5 molar. Now there are tricks that we can use, but it's dependent upon the K value. If the K value is in the vicinity of 1, either a little bit above or a little bit below, you have to use this equation. Actually, there's one other option, but I haven't got there yet. I'll give it to you in a minute. We're going to look at, I think we're going to look at, well, here's another one. If we follow that same procedure with different conditions, we get a different equilibrium position. And for these sets of conditions, we end up with 3 molar as our product. Okay. These are just steps in solving equilibrium problems. You got to have a balanced equation. That's absolutely essential. Then you write the law of mass action, the equilibrium expression, in terms of whatever you're going to use, molar concentrations or partial pressures. Then you set up your ice table. Okay? So you have write your equation, initial concentrations, And then if necessary, you calculate the Q to see which way you're going to shift, right? If one of these, if you've got values, if you've got concentrations for everything except for one of them is 0, then the shift is going to be toward the side with the 0. But if you have values for all of them, then you have to calculate the Q and compare it to the K in order to determine movement. All right. Then you define the unknown, right? And wherever possible, if the question asks you for the concentration of one of these terms, you try, if at all possible, to put the unknown value, X, for instance here, in that position, if you can. If you can't, then when you find out what X is, you've got to introduce it into the equilibrium expression here, these unknown expressions, in order to find out what the actual concentration is. So if we were after thiocyanate, then we would have to take that X value, put it in here, and that would tell us what thiocyanate was at the end of that reaction. And then after you've solved for the unknown, then you put the values that you've determined at equilibrium back into your equation to confirm that you have exactly the same number as K. You calculate the K from the determined values to confirm that that K is correct and your solution is correct. So here's several examples. I'm not going to go through these. You're welcome to. You find the equilibrium concentration of all species. Well, let's just do it for this one, right? If we say 8 minus 5, this one would be 3, right? And 10 minus 5, this one would be 5. At equilibrium, 5, 3, and 5. Okay? All right, here are the answers to the previous the previous slide's problems, in case you want to work them out yourself, and those are the answers so you can check yourself. Okay. So in this case, we've got the Haber-Bosch equation in reverse. So we're going to put 2 moles of ammonia into a sealed vessel, a 1-liter container. And at a certain temperature, we're going to say the ammonia partially dissociates according to that equation, right? So what's the question? At equilibrium, 1 mole of ammonia remains. Calculate the K. All right. So let's see. We can erase all this. Yep, we're doing good. Okay, what's this first step? The balanced equation. That's an equilibrium with nitrogen gas, hydrogen gas. So we need 2 here, and we need 3 here. Okay, that's the question. Is that balanced? No, this is balanced. All right, we have 6 hydrogens, 2 nitrogens, 2 nitrogens. So our equation's balanced. Now, we're going to calculate the K, so we have to know what our starting conditions are, what the change is, and what the equilibrium concentrations will be. They're all gases. So each of these terms will enter into the expression. Now, the K for this one is going to be different than the K for the Haber-Bosch reaction because it's inverted. So this K is going to be nitrogen to the first power hydrogen to the third power divided by ammonia squared. Okay. Now, starting conditions. We put 2 moles in 1 liter. So what's the concentration? It's 2 moles per liter, 2 molar. Okay. Let's see, I got too many zeros there, don't I? 2 divided by 1. There we go. What's the concentration of here at the beginning? 0. Okay. So we know which way it's moving. We're going to shift right in with this equation. We're told at equilibrium that we have 1 mole of ammonia remains. So what's the concentration of 1 mole at the end? It's in a 1 liter container, so it's 1 molar. Okay. So how did it get there? Well, it had to lose 1 molar. So that means for every 2 of these, you get 1 of those. That means we added only a half mole here, half molar, right? 2 to 1, 2 to 1. 2 to 3, it's easier once you get this one to say, all right, this is 1 to 3, so this would be plus 1.5, like 3 times that. Okay, now we can put our values here, 0.5 molar and 1.5 molar. So now we can do our calculations. Let's see, nitrogen is 0.5 molar. Hydrogen is 1.5 cubed. And ammonia left over is 1. Where? So we should be able to calculate that fairly simply. I'm going to say 1.5, enter 3, and then cube that. And 0.5 times that, and then divide by 1 is this. 1.688. But we can only, let's see, we've only got, so it's actually rounded off 1.7. That would be a correct answer if we had 2.00 moles of ammonia. But they're close enough for illustration purposes. Okay. That's the proper use of the ICE table. Now, when you learn how to use the ICE table, don't forget it when we move to the next chapters. You're going to be using this technique in all the chapters to follow. When we talk about acids and bases, you're going to use it again. When we talk about solubility products, you use it again. When we talk about complex ions, we're going to use the ICE table again. So don't learn it once and forget it. All right. We got a different equation here, so let's clean the board. And let me see. We're in pretty good shape. It's only 1020. So a 1 mole sample of dinitrogen tetroxide gas is placed in a 10-liter vessel and allowed to reach equilibrium according to the equation. And the K is given. What's the equilibrium concentration of dinitrogen tetroxide and nitrogen dioxide? All right. We need the balanced equation first. This is a decomposition reaction. It produces 2 NO2s. They're both gases, so the equilibrium expression is simply Yeah, in terms of molarity, equals 4 times 10 to the minus 4. And that's equal to NO2 squared over N2O4. I need a new marker. All right, so we set up our ice table. And we're given conditions. 1 mole of dinitrogen tetroxide in 10 liters. So what's the concentration? 1 divided by 10. And we've got 3 significant figures. Right? 1 divided by 10, molar. Okay? And none of this. So we know the reaction is going to proceed toward products. All right. So if we're going to calculate both of them, we can make X whatever we want. So in this case, if we lose 1X here, it's going to show up on this side as 2X. So this is 0.1 minus X, and this is 2X. Okay? Now, our expression is 4 times 10 to the minus 4 equals 2X squared. That was given out on the tube. Let's try another one. And this one is 0.100 minus X. Right? Just checking myself. Yeah, 1 squared. Okay. Okay. Now, here's the first trick that I'm going to show you. Notice that this value is extremely small. That means that the X, the loss of X here is going to be small. It's not going to move very far that side because it's 10 to the minus 4. So this X is so small, it's probably a lot smaller than 0.1, which means we can approximate this expression as 4X squared over 0.100. Right? I just squared this in the process. Squared that. And I got rid of that X because it's so small. It has little impact on this term. And that way, we can multiply 0.1 times 4 times 10 to the minus 4, which would be 4 times 10 to the minus 5 equals 4X squared. X squared equals 4 divided into that, which is 1 times 10 to the minus 5. And X equals the square root of 1 times 10 to the minus 5 equals. Which is 3.16 times 10 to the minus 3. And that's molar equals X. Okay? Now, this calculation tells us that we were right. This value is 2 orders of magnitude less than that. So it's going to have little impact on this value. But we haven't finished calculating yet. We need to say this minus that is our value. Okay. So I'm going to say 0.1 minus. And this is 9.9, no, 9.68 times 10 to the minus 2 molar. And this is 2 times that value. And this is 6.32 times 10 to the minus 3 molar. Okay? All right. 0.097. Move the decimal place 2 to the left. 0.097. And 6.32 times 10 to the minus 3. Okay. We were fairly safe in making that assumption because because this value is so small, we knew that X would be very small also. But there's a way to prove it and to satisfy any of your readers in case you try to publish this type of research. You just calculate, take these values, put them back in this expression, calculate that value, and compare it to this value. Is your calculated value within 5% of the known value? If it's less than 5%, then you're good. I think we've got some examples coming up. I believe we do. Hold on. No, we don't. Let's do the 5% rule just to show you how it works. Okay. I'm going to take these two values and plug them in right there. So I'm going to say this K experimental. Okay. So that would be NO2 squared, 6.32 times 10 to the minus 3 squared over 9.68 times 10 to the minus 2 to the first power. Okay. So let's calculate those values. 6.32 exponent, it's minus 3, excuse me, minus 3. And square it. And then divide that by 9.68 exponent minus 2. And I get 4.13 times 10 to the minus 4. Okay. So now what do we do with that number? It's not exactly this number, is it? What's the difference between those two? 4.13 times 10 to the minus 4 minus 4 times 10 to the minus 4 divided by 4 times 10 to the minus 4 times 100. So what would that be? Well, let's see. That would be 0.13, wouldn't it? Difference. 0.13 times 10 to the minus 4. 0.13 exponent 4. Okay. Divide by 4 and times 100. And that's 3.25%. Right? That's good. Now, the other thing you can do is once you've made this calculation right here and found that number with the assumption that it's very small and we can leave it out, then you go back, you take this value, you take these values, and you take the X value, this value, and you put that X in here. But you don't put it in there. You put it in the place where you made the assumption. So we put this value in here and then calculate the X based upon that. That's called successive approximations. And you can do this 2, 3, 4, 5 times, however many. Each time you do it with a new calculated X, you're going to get closer to the true value. For some equilibrium expressions, that's the only way to do it because they have powers of 6, 7, 8, 9, and there's no easy way to calculate those unless you have a computer that's programmed to do it. So successive approximations, is a good strategy. It works. In the future, we'll do one, maybe one of our problems, worked problems in the review document has some examples, and we can use successive approximations there. Okay. So that's ICE table, and it takes practice. So take advantage of that review document and practice how to do this, because you're going to need to know how to do this for the rest of the semester. Okay, Le Chatelier's principle. I think the A has a hat over it, doesn't it? Yeah. Le Chatelier's principle. Okay, we need to go back to one of the earlier slides where we said, what would happen if we added water? Or what would happen if we added hydrogen to that equation? We reasoned that it would shift. And Le Chatelier's principle is an expression of what we already know. What Le Chatelier said, he's a Frenchman, he said that if a system is at equilibrium and you do anything to disturb it and shift the equilibrium, the system will respond. And it will respond in the direction that tends to reduce the change. It reestablishes equilibrium. Now, when you introduce that stress, we call it the stress, when you stress the system, then the equilibrium position will probably change, but the constant will not. Okay, so what are different types of stressors that can be used to change the system? Well, concentration is one. We've already talked about that one. If you add a product or add a reactant, or if you subtract a product or subtract a reactant, then the system will respond. Okay. Oh, I got a video here.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay. So I put two of the reactions up here. I believe this was one where we added hydroxide ions, probably a sodium hydroxide that would work fine. And hydroxide combines with the iron to precipitate the iron, which removes it from the reaction and shifts the overall reaction to the left-hand side. This is called coupled reactions. And they're often used to demonstrate Le Chatelier's principle, because if you have aqueous solutions of all your reactants and products, this is a homogeneous system, then you can't get at removals. You can addition. Addition is easy. You just add a little more of this or add a little more of that, which is what our video showed us in the beginning. But if you're trying to remove something and show the removal, you have to use a coupled reaction that will effectively remove it. Or in this case, silver precipitates thiocyanate, and that removes reactants and shifts back to the left. We're going to be doing some of this in the lab, not this coming lab, but the one following it. Okay, that's one way to stress an equilibrium system, is change the concentration. Okay. So when we're talking about stress to a system, we can do concentration change, or we can change the temperature. In the case of concentration, let's see, let me erase this to make room. In the case of concentration, the K is still constant. We're working with the same K value. But with the temperature change, the reason that Le Chatelier's principle works for temperature is that the K will change. Okay? And that's where we get the shift. Now, how do we tell if a change in temperature is going to change the equilibrium? Well, there's a rule of thumb, right? We can do the quantitative measurements and calculate the K and determine which way we're going to shift. But the rule of thumb is much simpler. If you have a reaction where you have reactants and products, and you change the temperature, the easiest way to determine whether a temperature change is going to shift the equilibrium is to ask yourself, is this reaction exothermic or endothermic? If it's exothermic, you can put the enthalpy change as a product, right? Because you're going to feel it get warm. It's a product. So if we do that, right, we can put the heat term on that side. That means if we increase the temperature, we're adding that term. And that means, as written, the reaction will shift to the left. So an exothermic reaction will respond to an increase in temperature by shifting back to reactants. Now, if we cool it down, if we remove heat, then it will shift to products. The other possibility is if your reaction is endothermic, then the heat term goes on this side. In this case, if you increase the temperature, you're going to drive the reaction toward products. Or if you decrease the temperature, you're going to drive the reaction toward reactants. Okay? Very simple. Now, what if there are a few reactions that don't generate any heat? They don't have heat. So what happens when you change the temperature? Well, according to Le Chatelier's principle, there's no change in equilibrium, right? So there must be some effect for a non-endothermic and non-exothermic reaction, an isothermic reaction. There must be some factor that keeps the K constant even though the temperature changes, which is very rare. The other possibility is pressure. Or change in volume. Either way, we know from Boyle's law that if you change the volume, you're changing the pressure. And that's usually the way that we introduce pressure change to an equilibrium system, is change the volume. Okay, in that case, in order for this reaction to respond to a change in pressure, we need gases somewhere in that reaction. All of them or just one or more need to be gaseous phase. It only works, this pressure change only works for reactions that have gases in them, as reactants or products or both. The other condition is, what is the balance in stoichiometry? Say this is 1, this is 2, this is 3, and this is 4. Right? Coefficients. 1A, 2B's yields 3C's and 4D's. But if they're all gases, what we're looking for is the change in stoichiometric volumes. So this one has a total of 3 volumes compared to this one, which has 7 volumes. Whatever they happen to be, they can be liters, it doesn't matter. The ratio is important. So what happens if you increase the pressure on this equilibrium system? How is it going to respond? It's going to try to decrease the pressure. So if we squeeze it, increase the pressure, then it's going to try to make fewer molecules. So that would relieve the pressure strain. So it's going to shift back this way toward fewer moles, fewer volumes. If we decrease the pressure, it's going to go the other direction. So Under what circumstances would a change in pressure or volume have no effect? If, say, we had 1 and 2 here like that. So in that case, it'd be 3 here and 3 here. It doesn't matter what you do to the pressure or the volume, you're not going to change the equilibrium for that reaction. Let's see, do I have a video? Yeah, I do. Oh, no, that's the end, sorry. Now, what other conditions would not affect the equilibrium? Even if you had 1, 2, and back to 3, 4 here. 3, 4. That would be 7 there and 3 here. If you introduce an inert gas, inert gas is the safest, but if you introduce any gas in there, remember Avogadro said if you introduce number of moles of gas, you're going to increase the pressure. So if we introduce an inert gas in here, it's going to change the pressure, right? Does that pressure change affect the reaction? No, because the inert gas is not part of the reaction. It's not coupled at all to the reaction. So introducing an inert gas will not change the equilibrium. We could introduce another gas, as long as it was not coupled with this reaction, then it would not affect the reaction either. Okay, so those 3 factors, concentration, temperature, and pressure, are used, and this depends, this equilibrium, the K is still constant, and it depends on molar gas balance. Okay. All right. So I think that's the end of chapter. Yeah, that's the end of the chapter. So, I made a statement at the beginning. I'm going to repeat it now because I think 1 or 2 folks came in late. I've posted this revised schedule in Brightspace. And the only change is that since the governor has not made June 19th a holiday yet, and assuming he doesn't, we're going to go with this new schedule, which takes advantage of that day that I had put in there as a holiday. If it's not a holiday, then we're going to meet. So just pay attention to those changes right around June 19th and subsequently. And I posted this one in Brightspace also. So what I may do is make the old schedule invisible so that you'll be forced to look at this one. I think that'd be safer. So coming up, we're still going to have Thursday the 12th. We're going to do a review on this material, and then we're going to go in the lab and do the chemical kinetics experiment. So be sure and have your lab notebook prepared. All right, that's it, unless somebody's got question, comments. Okay, in that case, I'm going to stop the share and we're done for today.